Welcome students. Now we are ready with the new module of our video lecture. In this we are going to study something entirely different. Till now we have been studying the hypersonic aerodynamics, which is coming under a special subtopic, something called local surface inclination method. In the discussion of local surface inclination methods, we saw that we can get the quick results and we need only the knowledge of elementary mathematics. And for most of the part of its derivation, it requires only simple algebra. The reason behind this is all the previous methods we discussed, we did concentrate only a straight oblique shock wave, expansion wave, and local surface inclination methods, which are only localized phenomena. Try to understand. We are not trying to look into the ambient scenario, and we are not actually looking the entire flow field. We only localized, and we are concentrating in a very small point where we are trying to find out the coefficient of pressure. That's what we did. So they do not require any integrated knowledge about the flow field they are dealing with. So they only need simple calculation. They all fall under the category of something what you call local surface inclination method. However, if we want to know the flow and the behavior of entire domain, we must examine the entire flow field. In doing so, our mathematical requirement increases, which can be increases because the details of the flow field are governed by a system of conservation equation, which can be expressed by entire either integral or partial differential equations. This different approach in which flow field consideration becomes important is called flow field consideration. In this chapter, we shall deal with the approximate solution with flow field consideration of this equation for various hypersonic applications. So now with the words and the sentences I just said, it will become very clear that why it is called flow field consideration, because in this we not only deal with the phenomenon taking place in the flow field, we also actually deal with the flow field, the entire flow field, and we actually deal with the equations which define the flow fields. Those basic equations which govern the flow field, they are actually coming into consideration, and till now we have been ignoring that. There was a reason behind this. Actually, computation did not come until 1960. Up to late as late as 1960, the history of development of fluid mechanics has involved only two dimensions. That is the purely experimental or purely theoretical. With the advent of computational fluid dynamics after 1960s, a new third dimension was opened up, namely numerical computation. And today science of fluid dynamics is extended and applied by using all these three dimensions in coordination. Hypersonic flow analysis, since could not be put into experiments in the early days, it was done only by using simple theories, by applying the approximations. Since this approach was giving fairly good idea about the body in the hypersonics, they are still in use for getting quick and reasonable correct results. So before 1960, we are purely depending upon the experimental values or the theoretical values, and experimental also it was a little bit difficult. The reason was creating this hypersonic flows and then testing your bodies are not very easy at the time. So it was purely theoretical. Now purely theoretical means we have to deal with all these complex equations which are actually going to govern the flow field. So either you solve them with all these mathematical tools we have, or we go for the simple methods. Solving them was very difficult because the computation was not available and numerical methods were not available at the time. So scientists and researchers took the easy way and they went for the simple method, and these simple methods were giving very correct results. That's what we have been studying till now. They all fall under the category of local surface inclination method. They are still in use. It's not like they become obsolete. They are still in use because they give very good results, though they don't give logical answers and the logical explanation that why they are actually giving the correct results, because we are ignoring the flow field equations and all. Nonetheless, they are very useful results and they are still used, and we know that even the software which is actually helping in creating the in the hypersonic design, they also are actually embedded with these local surface inclination methods. There are more methods than we have studied actually, but at least these three are we have studied and they are still available in the gantries program. If anybody wants to work with this, they can actually use them. But now we have decided to go into the flow field consideration methods, and then we'll see that how it goes ahead. So here we are going to actually utilize the flow field equations. So let us first look into the governing equations. What are the governing equations which actually define the flow field? They are not new. Maybe the equations may be new, but the concepts are not new. So these are the governing laws: the law of mass conservation, the law of momentum conservation, and the law of energy conservation. We have already seen in many. We have been studying this since the day we joined and started studying engineering. In the fluid mechanics, in the aerodynamics, everywhere we study the same thing, and same thing is applicable here also. There is nothing new. The laws are same basically. Equations may be a little bit more complicated than what we saw earlier, but energy these laws are same. So we are not going to into details. There is one more concept which is being utilized here, that is the law of species conservation, and this is coming because of the thermal effect of viscosity. What is it actually? Now suppose in a normal case, when the thermal effect is not taking place, we have nitrogen, oxygen, hydrogen, or maybe CO2, or some other gases which are actually maybe the ozone. All these things are actually flowing. And at the end of when it is coming out in our control volume, we still have nitrogen, oxygen, hydrogen, CO2, and O3. So the simple law of mass conservation is enough to deal with them, because whatever is going in is coming out, so mass is conserved, it's not dissipating anywhere, so we don't bother. Whatever is going in is coming out as it is. These are the situation when we have a low temperature flow. When the temperature goes high, then what happens? This side maybe our nitrogen is going, and oxygen is going, and hydrogen is going, and CO2 is going, and O3 is going. On the other side, we may get that instead of hydrogen, nitrogen directly, we may get nitrogen atom. You have nitrogen molecule, nitrogen element, nitrogen atom, and oxygen atom, and hydrogen atom, and there's a possibility that we may get OH. These hydrogen and oxygen not only got dissociated because of high temperature, they also start joining together. So the entire flow which is coming out may contain even the OH radical, or maybe something like CO. So how to actually find equationalize this situation, that whatever is coming out is the same thing whatever is going in. So instead of looking directly into the oxygen, nitrogen, and all those things which can actually break down and dissociate because of the high temperature involved in this region, we start looking into the the atoms of all these things, because we know that these changes are chemical changes. High temperature is good enough to bring about chemical changes, but this is not good enough to bring about nuclear changes. So we just concentrate that actually what is going in actually 2 of nitrogen atom, and 2 plus 2 4 of oxygen atom, and sorry 4 plus 4 something like, not just 4 from nitrogen here also. So uh, 2 plus 2 4 plus 3 7, so 7 oxygen atom, 2 hydrogen atom, and 1 carbon atom. So this is going in. So we now try to concentrate that these things which are going in, they must come out. It's not just so these things are conserved now, not the entire these things or these things. When nitrogen is going or carbon dioxide is going, this may not come out. Possibility is there that even the CO may be available because of dissociation and reassociation kind of thing. So these are the species. So we not only in this case trying to concentrate on the mass conservation, they are also trying to concentrate that the species should remain constant. So now number of oxygen entering must be equal, must be that number of oxygen coming out. Mass conservation alone is not able to give this thing, because if you talk about sometimes it may possible that actually like nitrogen has got molecular weight is equal to some 14, so 28, something like 28, and plus something like 2, something like 2h, so it's equal to 2, so it's equal to 30. So if 30 gram is getting in, this 30 gram can come out by fulfilling the entire mass conservation law, mass conservation equation, but still there may be not nitrogen and hydrogen, rather some different species of the same mass, because dissociation is happening. Instead of nitrogen and hydrogen coming out, if it is if N2 plus H2 is entering, so maybe something some different like NH NH something like NH plus something else is coming out, like oxygen may come out plus something like carbon may come out, and this still if sums up some in some way equal to 30 gram, that will satisfy the mass conservation. But that's not what we want, because something has happened in between. Otherwise our nitrogen will not change into oxygen or carbon dioxide. So we actually now concentrate on a third law called law of species conservation, if you are dealing with the high temperature, and we know that hypersonic regime is a high temperature regime. So our governing equations are not only governing laws are not only these 3 laws which we have been dealing till now. There also comes one more law, that's called law of species conservation, and this is coming because of the thermal effect of viscosity, and I think now students should be aware till now that why this is important. Sorry, there was a malfunction in the slides. Now let's go to the equations. They're the governing equations. This is very easy to recognize. I hope we have been seeing the same equation again and again. This is this is the mass conservation equation. This is talking about the time derivative, or these are the space derivatives. Then we have momentum conservations. So these are the governing equations. This is the momentum, this is the continuity equation, and these are the 3 momentum equation in x, y, and z directions, and these this is actually talking about the time derivative, and these are space derivatives, and this is the pressure gradient. Now by looking at it, we can easily say that we have actually ignored the viscosity because we are still dealing the inviscid flow, and also the body forces have been ignored here. So by doing all these things, this momentum equation turned out to be like this. Then we have the energy equation. Energy equation, if energy is conserved, we just go into the mode of understanding that the entropy is conserved and there is no loss of energy, so entropy remains conserved. So we write S, and if entropy is conserved, then it should be like this. This is the time rate derivative entropy, and these are the spatial derivative of the entropy. This is something similar to what you see in the mass conservation. Now the question is, normally we don't deal with the entropy, so we don't have entropy relations, or even if it is there, we have this entropy relation here, like S is equal to Q by T, or delta S is equal to delta Q by T. This gives the entropy. But we don't normally deal with entropy relations, so we try to change it into simple relations of pressure, temperature, and density. These are our parameters we normally deal with. How to change it? So the concept is that if entropy is conserved, then an isentropic relation or isentropic system or situation is also essentially adiabatic. Because something like isentropic relation is nothing but adiabatic relation plus reversible reaction. So an isentropic relation is essentially an adiabatic relation as well. This had to be here like this. So we, instead of dealing with S, we deal in P by rho to the power gamma, which is actually a if it equal to constant. This is the relation for adiabatic. So we now can replace the S by P by rho to the power gamma. So now we replace the entropy with the expression P to the power P by rho to the power gamma. That's actually coming from the adiabatic relation. So now after replacing S by this, we got this equation, and this equation now we are going to actually use in understanding and dealing with the flow field in the case of hypersonic flow. What else? This is not enough, because we know that we are dealing with the differential equations. So when we integrate it, we'll get some constants, and these constants will be solved or will be known, made to known only if you know the boundary conditions. So we'll need the boundary conditions as well as initial conditions. Initial conditions we'll ignore because there is we have here time derivative. So we'll deal only the steady flow. If you deal with the steady flow, this time derivative will vanish. So if the time derivative is not there, only we have special derivatives, then only boundary condition is required, and we don't need the initial condition. Now let us just try to non-dimensionalize the equations we have seen or we have just gathered till now, for which actually are governing the flow field. We come to the governing equation again. Now for non-dimensionalizing, we need some of the reference parameters, so that we can non-dimensionalize our the variables on the parameters and all these relations. So for the sake of for non-dimensionalizing the length of in the flow field in x, y, and z direction, we use L. L is the length of the body, which is actually under consideration. So L dividing x dividing by L actually become x bar. The x bar is the non-dimensional x direction, length in x direction. Similarly, we can do with the y as well as z. And Then for the sake of u, we take the free stream velocity, that is v infinity, as well as v w also. Now what comes for the pressure is we need uh, some kind of that equation or some kind of expression which is having a dimension of pressure, and for that we select rho v square, which also we call actually the dynamic pressure. 1 by 2 is missing here, that's actually the value, but what we need is like the dimension. So rho v square both at the in the free stream level are actually chosen to non-dimensionalize the pressure, and density anyway the rho infinity is enough for that. Now one question arises, why not we take the p infinity? For the sake of, if p is there, we enter the p infinity. There is a good reason behind that. Actually we do the non-dimensionalization of the equation, so especially if some complicated equation is there, to get some help and ease in solving the equations. And as we proceed ahead, we'll see that taking this particular value for the non-dimensionalization of pressure is actually helping. If we take p infinity here, no doubt we can actually that also will be there. That also will be a non-dimensional parameter, but that will not help us in solving and also making the life little easier. So after having some kind of calculations or estimations and observation, scientists have found that this is actually helping. So we go for this expression rho v square as the non-dimensionalizing reference value for the pressure. Now this is the continuity equation, and when we just apply those non-dimensionalizing references in the continuity equation, we found that the entire equation comes out of it, and then there becomes a factor of this, and right hand side is 0 anyway. So even if something is there, the entire equation is multiplied by rho v by L. How we see that? So now we have first here sorry, we have the equation something like rho u by rho x plus rho v by sorry rho I plus rho w by rho z equal to 0. That's what is our governing equation or the continuity equation. Now we just write here something like, just look at carefully here, rho x, now rho upon rho naught, to non-dimensionalize the rho, then we write rho naught here, and u is here, we write v infinity to non-dimensionalize it, so we write b infinity also, and to non-dimensionalize the x we write L here, because L is the non-dimensionalizing reference parameter for dimension for the length, so any length in any direction, so we write L here to make sure that they determines balanced. This becomes actually your first term here. Second term also will give the same thing here, because rho v is there, for rho we have to write rho naught, for v is v naught, v infinity, and for y you have to write L. So here also will come the similar kind of thing, like rho upon rho y upon L, rho upon rho naught, and v upon v naught. Similarly we can have there rho upon rho z by L into rho upon rho naught and to w upon v infinity. So we have this thing, and this is equal to 0. This whole thing comes out as a factor. This can be ignored. So after that our governing equation will become like something like rho bar rho bar u bar divided by dou x bar plus dou uh, rho bar b bar by dou y bar and so on like that. This way we can actually now non-dimensionalize our continuity equation. That's very simple. Now the momentum equations, you go this way. Momentum equation. So these are the momentum equation in the x, y and z direction. So x momentum is the x momentum, the y momentum, or you call it z momentum. They are having this as a factor. Students can try anyway. I'll give a little demo that how this comes out here, and there here you will find it's advantageous that this becomes the fact. This becomes actually the common factor for the entire equation, and that's why you will realize that why we took this rho v square as the non-dimensionalizing reference expression for the pressure. Let us see how it goes ahead. Now that the momentum equation is given by rho u x plus rho v by dou I plus dou w by dou z is equal to minus dou p by dou x. Now we have to non-dimensionalize this thing, so we have to write first rho by rho infinity. So we write one rho infinity here, and then u by v infinity. So one v infinity is here, and then we have again one u inside. So you write u by v infinity. So we write v infinity square, and divided by dou x by L becomes actually L. This is our first term. Second term also we'll see that rho v is there, so we write rho upon rho infinity and v upon v infinity. So the same thing goes here, and then we have inside v upon v infinity by dou I, and similarly we have rho upon dou infinity, and then w upon v infinity, then dou w by v infinity divided by dou z, and then equal to, now this comes here. So for non-dimensionalizing p, we have to write dou p by p infinity, oh sorry, not p infinity, rho infinity and v infinity square, and divided by dou x upon L. We will be here also, L will be there. Now it would have been clear here to the student that actually why we did not take the p infinity for non-dimensionalizing the p, the pressure, because in that case we will not have a common factor, something like this common factor will not be available there in that case. So now this whole equation comes here, so in this case it will become actually dou bar u bar dou u bar by dou x bar plus rho bar v bar minus dou p bar by dou x bar. Nice equation we got here. This is our x momentum equation, this x momentum only. Similar treatment we can do for the y momentum as well as z momentum. They all look same here, and our common factor will be always like this, so it comes out, and then we have same thing here. We have these equations here available. These are these common factors can be taken out and then we can be discarded. So these are our equations which are going to utilize non-dimensionalized governing equations. So these are the equations we have, this continuity equation and 3 momentum equation. Now what happened to the energy equation? Let's see that. That's also the equation we have. So this is the energy equation we are dealing with. Now let us see how it goes ahead. In fact, looks like that nothing is on right hand side. So whatever comes here will be actually discarded out. But let us see what comes out here. This is the. Let us just try this. The energy equation is actually something like sorry, it's going there. So we have u dou by dou x p upon dou to the power gamma plus v dou upon dou I p by dou to the power gamma z p by to the power gamma is equal to 0. This was energy equation we have already agreed with. Now this has to be actually changed and non-dimensionalized. So let me start taking it. U will be non-dimensionalized by putting v infinity here. So we multiply by 1 v infinity here, and then dou upon dou x by L, so divided by L, p upon rho v infinity square, so we have cube here, into rho infinity by rho upon rho infinity to the power gamma. So we put here rho infinity to the power gamma. Similarly, we do all these things. This becomes actually u bar dou upon x bar p bar by rho bar to the power gamma, and similarly others can become actually v bar dou upon y bar p bar by rho bar to the power gamma, and w bar dou upon dou z bar p bar rho to the power gamma to 0, because this will be the common factor coming out of it. So now we saw that. Similarly we can write so now we have non-dimensionalized the energy equation as well. I'm sorry, actually when I showed earlier there was a little typo here, and I got corrected. I corrected it actually. This gamma was missing here, L was missing here, but they will be there because we have to non-dimensionalize x, y, z as well as p rho to the power gamma also. So this will be the common factor which we can take out, and finally we'll have this equation as the non-dimensional equation. They are still in the partial differential equation format, and we definitely need boundary conditions to solve them. Initial condition not required anyway, because the time derivative is gone. Only the special condition is required. So what are the boundary conditions? Let us see the boundary conditions now. The very first boundary condition we'll go there is no penetration condition. Normally whenever we deal with the fluid flow, we actually always put one condition, and we put one universal type of condition, that is no slip condition. That condition will not be here. The reason is this, we are dealing with the inviscid flow right now. So viscosity is 0. Viscosity is 0 means there will be no boundary layer and no shear stress available on the surface. But still we cannot expect the flow or the fluid to enter into the surface of the solid. So there will be no penetration. It means the flow, when actually when it reaches the solid boundary, its velocity will be tangential to the solid surface. It can only glide, it cannot enter into this. So it means that there will be no normal velocity. So the normal velocity component at any location on the surface will be 0. So in that case, if we take the dot product of the total velocity and the normal and the normal vector on any particular point on the surface, then it should be 0. This simply tells that there is no normal component of the velocity. In some particular cases, which we are not dealing with, if there is some kind of velocity transfer or some kind of transfer, is the mass transfer is taking place on some porous surface, or maybe some the surface is absorbing the fluid force by some mechanism which we are not dealing right now. In that case, this will not be 0, and then the v vector into a dot n vector n cap should be equal to actually vt, the transfer velocity by which the fluid is transferring into the solid. That will be actually written here. Anyway, right now it's assumed 0 because there is no penetration is there, and so no penetration condition tells that there is no normal velocity at any point on the surface. This can be broken into 3 components like u, v and w, and this can also be actually non-dimensionalized. So u dash, v dash and z dash are there, and they'll be dealing good in the case of our non-dimensional treatment of the governing equations. Special conditions comes from the shock, because we are dealing a flow after the shock. So basically we are dealing into the shock layer, the flow between the shock and the solid boundary. So there is a shock layer. So shock layer is bound by solid surface on one side and the shock on the other side. So other side conditions are basically coming from the shock boundary conditions. So shock boundary conditions are coming, and then at the shock you have the pressure difference P2 by P infinity. P2 is the shock, the pressure after the shock, and P infinity is the free stream pressure, or normally you take P1, but we have now converted P1 into P infinity. All the P1 values are actually the free stream values, or the one values are free stream values. So P2 by P infinity this is the normal. This is the general relation for the pressure ratio across an oblique shock of shock angle beta given here. This is exact relation. First of all, we saw that this is a density ratio. So pressure ratio and the density ratio both will be applicable on the shock boundary condition, and they will be affecting the governing equation, and they will help us in finding the constant when we integrate them. Now we have this other condition, the velocity conditions. We know the velocity u and v. U and v are not perpendicular and that along and perpendicular to the shock, whether they are along the free stream velocity and perpendicular to the free stream velocity. So they are also having this relation. We have seen this relation long back while dealing with the local surface inclination methods. So we are aware with this. These are the 4 equations which actually give us the boundary condition on the other side, on the shock boundary side. On the solid surface side, we have already seen that the velocity will be the normal velocity will be 0. Now this boundary condition 2 needs non-dimensionalization. So let us try to non-dimensionalize this. No penetration condition, we have already seen the non-dimensional value or non-dimensional equation that just u, v and w become non-dimensional, and the common factor, if you take this reference value, reference velocity divided by v infinity, is again common, and then it can become multiplied with 0, it becomes 0 actually. So we have already done the non-dimensionalization for the penetration condition, no penetration condition. We have seen this thing. Let's go to the shock boundary condition P2. Now P2 is the pressure ratio, pressure, non-dimensional pressure after the shock. How it comes here? This is looking a little bit different. We'll deal with this thing. Let us see how it goes ahead. Now the pressure ratio across the shock is given as P2 by P infinity, and that is equal to some value, doesn't matter, but let us see how it goes ahead actually. So P2 by P infinity, we try to non-dimensionalize P2, so P2 by rho B infinity square, so we write here rho infinity B infinity square, and then P infinity comes here. This was so this is the one is coming here now. This is actually equal to B infinity square by P infinity by rho infinity, and then this one already we have P2 bar, and this is again equal to P infinity square by RT, because P by rho is equal to RT. From the equation of state, and then we have P I'm sorry students, I'm suffering from some kind of cold, and I'm creating this videos in emergency because you need this. We have P2 here redimensionalized, and V2 by RT. Now if we just write gamma here and gamma here, this becomes actually gamma B infinity square by under root gamma R T, in fact T infinity whole square, and then P2 bar. That's actually equal to, this particular factor is equal to gamma M infinity square, and then P2 square, P2 bar. So this value, which is actually given already, we have seen that across the shock, is nothing but equal to this. So this can be converted to P2 bar, actually whatever is there on the side divided by 1 by gamma M infinity square. And let me see what was given there. P2 by P infinity was given equal to actually 1 plus 2 gamma by gamma plus 1 M infinity square sin square beta minus 1. This was given for the equation across the shock. Now we divide by gamma M infinity square. What it yields? We'll see that. This yields actually equal to P2 bar equal to 1 by gamma M infinity square plus 2 upon gamma plus 1 sin square beta minus 1 upon m infinity square. That's what we got. So this is the value. This is the value we have got, and that's what is written there. So it is a non-dimensional form of the boundary condition, the pressure ratio across the shock actually. So this is what is used here. We found that. So we have non-dimensionalized the pressure ratio across the boundary across the shock boundary condition actually. Now the other shock boundary conditions, velocity and the density, are actually given in the non-dimensional form itself, because the density ratio was given and the density ratio with density with respect to rho infinity was given. That's what we selected as the non-dimensionalizing reference value, reference parameter. Similarly, it was in case of u2 it was v infinity, because of v2 it was v infinity again. So they are already in the non-dimensionalized format. We don't have to do anything. Only pressure was required. We have done that. Now these non-dimensionalized formats are actually again looking very complicated. So what we are doing is, now we are trying to actually apply the approximation. We know that we are dealing with the approximate methods. We are calling approximate methods. So somewhere it is approximation is coming. The approximation is the m infinity change tends to infinity. It's a very high value because we are dealing with the supersonic, hypersonic Mach numbers. So if the m infinity change to infinity, what we get here is the pressure ratio becomes like this, and density ratio becomes like this, and the velocity ratio as well. They are all these values are like this available here. Students should try. I think it's not much difficult to get these values. In fact, we just apply the m tends to infinity and then take the limit. It's limiting value. We'll come out with these equations. If you have any problem, then you can mail me, or we can just next class you can ask me. Otherwise, I think this is enough. This is good enough to understand this. So I'm just leaving it here. These values we have got now after applying the approximation of m tends to infinity. Now Mach number independence. Mach number is actually affecting the flow, no doubt about it. But when the Mach number becomes very, very high, the flow properties start showing a behavior of something like non-influenced by the Mach number. So that's what we are going to discuss in the couple of slides now, how it actually happens. Let us consider upon a flow of a case of a flow over a wedge and a cone of something like 15-degree half angle. It's clear that for the supersonic Mach number, Cp decreases rapidly as m dot is m infinity is increased. We say that if m infinity increases for the subsonic flow, it actually decreases rapidly. Sorry, for the supersonic flow, if it increases, it decreases, and for the subsonic flow, if it decreases, then it increases. If for the subsonic flow, if m decreases, then Cp decreases too, because negative here. And in the supersonic flow, if m increases, then Cp decreases, because it's a positive here. In both the cases, we have a critical point, that's m is equal to 1. M is equal to 1. This turns to be 0, this also turns to be 0, so it becomes a very high value. So as the m approaches 1 from either side, either for a very high value to 1 or from a very low value to 1, these two values for the supersonic subsonic tends to become asymptote or something like become very infinite, very, very high value. And on both the sides they normally decrease. That's what we have seen this thing. So these are basically Prandtl-Glauert relations. And these two relations are basically telling that the Mach number has a direct impact on the coefficient of pressure in the supersonic as well as subsonic regions. Let us see how they behave. So here actually you can see that graphical resolution of something like also available here, that for this is for the subsonic region. As the Mach number increases and goes towards unity, it becomes high and high. So if Mach number decreases, the CP will keep decreasing, and minimum value will be 1 actually. And in the case of supersonic flow, supersonic region, supersonic after Mach number is equal to 1, this tends to become infinity at Mach number is equal to 1 again, and start from here, and then it actually start decreasing and keep decreasing. There is no end value for this thing. There is no limiting value for this. Keep decreasing and approaching towards the zero value. Yes, it will not become negative, but keep decreasing towards the zero value. So Mach number is actually affecting the supersonic as well as subsonic flow greatly, and this is the relation given by the Prandtl-Glauert transformation. In the case of hypersonic flow, the decrease diminishes. It actually decreases, no doubt about it, but decrease diminishes considerably, and CP appears to reach a plateau at m infinity becomes large. So if m infinity is large enough, the coefficient of pressure start attaining some constant value, and it actually stopped getting influenced by the Mach number. In other words, for the hypersonic flow, as the Mach number increases to higher and higher values, the value of CP becomes relatively independent of the Mach number. It's not decreasing or increasing. It's actually the Mach number is losing the control over the CP. This is the essence of what you call Mach number independence principle. That's what we are discussing right now. So at the high Mach number, certain aerodynamic quantities such as pressure coefficient, lift and wave drag coefficient, and flow field structure such as shock wave shape and Mach wave pattern become essentially independent of the Mach number. Indeed, the straight Newtonian theory becomes totally independent. And look at here, Mach number. Although modified Newtonian theory exhibit some dependence and hence variation with Mach number. These are the values given for this flows. So for the cone and for the wedge is available here. If we try to find out, use the Newtonian theory, then it's going to be completely free of Mach number. It gives constant value, doesn't matter. It doesn't consider the Mach number actually. The other values, they consider the other method, like we saw that Prandtl-Glauert relation or CP value. They consider the Mach number, and as the Mach number start increasing in the initial ranges, from you can see that from up to 4, they have a huge change from very high value to the something very low value here, from 5, 6 to coming 0.4, 5, 6, coming to like this actually 2. So there is huge effect in this region. But as the Mach number goes very high and high, they start attaining some kind of constant values, and they are still above the Newtonian values, but they start becoming flat, and Mach number loses the control over this thing, and the parameters become actually Mach number independent. Newtonian theory is completely free from the Mach number, but the modified Newtonian theory and modified Newtonian law or the equation actually is affected by the Mach number, because the CP max, it contains the CP max, and CP max depends on the Mach number. But CP max also start exhibiting the independence of the Mach number at a very high value. This is what the CP max is there. So CP max also becomes independent at a very high value. So the Mach number independence is more than just an observed phenomena. It has mathematical foundation which confirms its existence and behavior. We have already seen the Mach number, the non-dimensionalized forms of the boundary layer conditions. No boundary layer. The boundary conditions. at a very high Mach number with the approximation of m infinity goes to very high value, or m infinity goes to infinity, tends to infinity, they become independent of the Mach number. We have seen already, and this graph also is actually showing, and it is not just a observed phenomena. This actually happens, and this can be proved mathematically also, which you have seen already. Now let us see just something like why it happens and how actually is happening. So the first thing is laws of conservation. They don't include Mach number. So the law of conservation, we have seen that those law of conservation which are yielding the governing equations like conservation of mass, conservation of momentum, and conservation of energy, they actually don't talk about Mach number. They talk about velocity, but they don't talk about Mach number. So Mach number is already not influencing those values, those equations, all these things. So the governing equations are already free from the Mach number. Now they have two boundary conditions. One at the solid surface, where we assume that there is no penetration and normal component of velocity is 0. Again, it is free from the Mach number. Mach number has nothing to do. It two boundary conditions, and one is the no surface penetration boundary condition, and definitely it has nothing to do with the Mach number. So Mach number is not affecting here also. Mach number is basically affecting in the second shock surface boundary conditions. And these shock surface boundary condition also we saw that at very high Mach number become actually free from the Mach number. Yes, in the subsonic and supersonic level they are affecting, but in the hypersonic range they are not affected by the Mach number. So as a whole, we saw that even the conservation laws, the governing equations, and the boundary condition equations are actually free from the Mach number. So at the the Mach number is in the hypersonic regime. So the entire flow is actually free from the Mach number. Mach number is not affected. You can see that these are the boundary conditions at the high Mach number. Pressure ratio, non-dimensional pressure ratio, free from the Mach number, and density ratio. Density ratio basically tries to get a this also is still affecting with the beta. With beta will actually keep varying, but this is taking a constant value, something that will be something equal to 6 if it is gamma is equal to 1.4 for the air. And beta also looks like will keep varying, and if beta is beta may inject the influence of the Mach number in the pressure and the velocity, but actually beta is also taking a constant value. Beta becomes actually free from the Mach number if the Mach numbers go very high, and we have seen already we have driven the equation and got the mathematical proof that beta becomes actually just for the gamma is equal to 1.4 20% more than the theta. Theta is a constant value. Theta is the deflection. Theta is not depending upon the Mach number. So beta also becomes free of the Mach number. So as a whole, the entire set of the governing equation as well as the boundary condition for the hypersonic flow regime are actually free from the Mach number, and this is what we normally call it the Mach number independence principle or the theorem for the hypersonic regime. So if the governing equations and the boundary conditions are free from Mach number, then the solution of the problem 2 will be free from Mach number. This is a very no logical statement. Therefore, when the free stream Mach number is sufficiently high, the non-dimensional independent variables become essentially independent of Mach number, and that's what completes the essence of that's what completes the entire understanding of the free stream Mach number independence. Now here is a small example of the experimental as well as the theoretical values calculated for the flow, the hypersonic flow over the cone plus cylinder combination and the sphere. So here is a cone. In the cone we have the 60 degree is the full angle, so the 30 degree is the semi angle of the cone, and then we have a cylinder. A sphere is a sphere anyway, so all these plus signs are actually the cone values, and the 0 and the cross sign are actually the sphere values. They go up to here in the similar fashion, then they start falling down. They start falling down something like near equal to 1. They start falling down, you can see that. As the Mach number keep increasing, then they start decreasing, and after certain time they start taking a constant value in the case of a sphere as well as cone and cylinder. Now this sphere is attaining the constant value or becoming Mach number independent sooner than the cone cylinder combination. You can see that it actually is keeps being affected up to some certain distance, and then again it also starts showing the independence, but it takes some little longer actually. What is the reason? Look at these governing the boundary condition. Governing equation anyway free of Mach number, so only the boundary condition can affect it. The boundary conditions are the non-dimensionalized boundary conditions, and are actually containing a factor called m square sin square beta. This m square sin square beta is high for the sphere than for the cone cylinder combination. So m square sin square theta sin square beta is already at a higher level, and it reaches the independence Mach number, where the Mach number influence becomes ineffective for the phenomena and for the CP calculation, all the things, sooner than the cone and cylinder combination. So a sphere becomes actually independent of Mach number sooner than the cone cylinder, because m square sin square beta is higher for sphere than the cylinder and cone combination. And this m square sin square beta appears in all the three equations. You can see that even here it is there, and it is here also, and it is actually here also. Even in the pressure relations, we this is the non-dimensionalized pressure. We can here see that the m square sin square beta is existing here also. So if you take the common here, m square comes in the denominator and becomes m square sin square beta minus 1. So m square sin square beta is existing even in the pressure non-dimensionalized pressure ratio. So because of this m square sin square beta existing in all the relations, and this value being higher for the sphere, the sphere starts showing Mach number independence behavior sooner than the cone and the cylinder combination. Again, but the pressure and temperature alone, this is not the non-dimensional value. This is not the non-dimensional temperature and not the non-dimensional pressure. The pressure and temperature, the absolute temperature and the absolute pressure, still remain Mach number dependent. We have to actually understand that. If the Mach number keeps going high and high, the pressure will keep going high and high. It will not be affected. It will not reach any plateau. It will not reach any constant value, and temperature will also have the same. So despite other parameters are showing some kind of independence, the pressure and temperature will have some value. Now here also we can have little kind of extra information that why we deal with the non-dimensional parameters. In the case of dimensionalized parameter, or the parameter with the dimension, temperature normally we are not dealing with, because we are not dealing with the thermal effect right now, but the pressure will give a non-independent concept. Pressure will depend upon the Mach number, but even if the Mach number is very very high, but if you are dealing with the non-dimensional pressure here, non-dimensional pressure, then by the very high Mach number, they also attain some kind of standard value or some kind of constant values, and then the entire boundary condition and the entire governing equation are actually free from Mach numbers, or life becomes easy. We can easily solve that. That's what we saw that. So we have reached the first module about this approximate method. We dealt with the governing equation as well as governing laws, and we also saw the non-dimensionalization, plus we also saw the concept of Mach number independence relations and Mach number independence principle, which actually affecting the hypersonic flow regime. In the next session we are going to study the hypersonic small disturbance theory, and till then keep up. Thank you very much.